So this presentation that we decided to put on today it's really where do we see nuclear fitting into sustainability overall as it relates to data centers, but also just and beyond data centers. Data centers is my passion and what I really enjoy talking about and designing. So that's really the basis of this. But what we're going to talk about will impact much greater than just the data centers themselves. Okay. So first, let me introduce myself. People that may not know me, my name is Jimmy Sneed. I'm the managing principal and a managing director of critical facilities for WB Engineering. I've been in this business for about 30 years. I'm an electrical engineer by trade, and so power is near and dear to my heart. And this particular topic became very interesting to me. And the reason I really wanted to put this presentation together was to raise awareness about nuclear and maybe educate some people on some things that are some misconceptions and where I think that this industry is going and where that nuclear can help us as a planet going forward. And today is let Michael introduce himself as well.
Thanks, Jimmy. Excited to be here. My name is Michael Crabb. I'm a senior vice president with a company called Last Energy. We are a micronuclear power plant developer. We are a U.S. company developing projects in Europe. My background, I'm actually an engineer by education as well, although I never practiced. I took the FE, but not the PE. I had a decade of energy market experience on the buy side. So the first 5 years of my career with a power and midstream gas focused private equity fund. And then the next 5 years with a corporate IPP, independent power producer. We owned a number of gas-fired generation, wind and solar developments, and battery development, and then power scheduling. My role at Last Energy is to originate our power purchase agreements. I lead our project development activities and ultimately the project financing. So excited to share more about what we're doing and how we're trying to bring solutions to the data center space.
Thanks. So as we get started, I wanted to share a quote. It's from Marie Curie, and I think it means a lot, I think, in the way we look at nuclear today, especially some of the misconceptions and things. So it really ties into the nuclear industry as I see it, which is nothing in life is to be feared. It's only to be understood. And now is the time to understand more so that we can fear less. And so she came up with this quote when in the early discovery of radiation. So I thought this was very poignant. So before we talk about the nuclear engineer itself, why are nuclear reactors themselves? Why do we need and why are we worried about nuclear as a industry? So first thing we got to think about is what's driving the power demands. So go ahead, Vic. So the three things that really I see driving our power requirements over the next 10 to 20 years are data centers, which we're here to talk about, but also electrification of equipment and EV charging. The first thing we look at data centers, for example. So today, data centers are using about 250 terawatt hours of power, which is pretty substantial. And over the next 10 years, it's going to increase by at least 10 times. They feel I even see some numbers that maybe have that even going higher. And by 2030, 25% of all the power produced on the planet is going to be used by data centers. So that our industry is really driving the need for more power. And where are we going to get that power from? One more thing. So just to put this is a little thing to put it in perspective. We've shown this before, but data centers today use more power than some smaller countries, and really not even so small when you look at Egypt and South Africa and such. I mean, that's pretty substantial, and it will actually be more as we progress over this next 10 years, over this next couple of decades. And then a thing that we've all seen on the news, our current administration talking about even our stoves in our homes and things are going to go away from natural gas, water heaters away from natural gas. Well, it's already happened in a lot of states, even on the commercial side, like California, New York, Massachusetts, Washington State. Anything new that you build, they're pretty much driving us away from using natural gas as a source. They want to get away from fossil fuels. So the only way to do that is to electrify that. So as all these new things become electric, obviously it's going to tax our grid and it's going to tax require more power. Where are we going to get that power from? And then the final thing that's really driving it is EV charging. As we drive around, everybody sees the Tesla stops, the EV goes, all of these things that are popping up in our retail centers for private charging of our vehicles. But then also the ones that you might not be as familiar with are people like FedEx or companies like FedEx and UPS that are going to electrify their trucks. So they're building these huge fleet charging facilities. When I first started in data centers, a 1 megawatt data center, which was big, when we first started this business. And now we're seeing EV charging, fleet charging that's 8-10 megawatts just to charge vehicles. So obviously that's going to be a huge driver for our electric grid going forward and how we're going to get this power to everybody. So the next part we wanted to talk about, we're going to need all this power, but on top of that, we've got a serious drive to get away from fossil fuels. And so how do we create this new power and at the same time reduce our carbon footprint? So Michael will we'll walk you through a little bit about where we see that going.
Yeah, thanks, Jimmy. Jimmy showed a few slides sort of projecting energy demand forward. I think it's also useful to look at the exponential increase in our energy consumption as a species historically. And it really starts to put it in perspective, both how dramatically we've increased our energy consumption, and two, how closely tied that energy consumption is to human prosperity, right? Like our ability to manipulate and channel energy for the good of humankind is a key aspect of how long we live, how comfortable we live, our ability to do things besides work in the fields, right? And it's opened up this huge opportunity across the developed world for sure, and increasingly the developing world, and that is just going to continue. And so I think that's sort of the top line of this chart. And the other thing to note is we've never successfully transitioned from any specific energy source. We've just gotten better over time at identifying more efficient energy sources. And now we recognize that those energy sources also need to be sustainable. And so there's very few alternatives that provide those three things, right? An increasing source of energy, a sustainable source of energy, and a scalable source of energy. And so as you think about all of these different options, and many of them are listed here, and there's lots you can, on social media or Google or the, the papers, you hear about all of these new breakthroughs and crazy technologies. It feels like every few weeks. I think when we think about kind of the system approach to delivering energy, both electricity and other sort of workable energy like process heat, we always need to trade off a set of competing priorities around risk, reliability, supply security, and cost. And none of these sources are perfect on every metric, right? And so that's part of the portfolio approach. So if you go to the next slide. So here's kind of a few of the sort of common technologies. I won't go into all of them in depth. I'm certainly happy to talk about my experiences with each of these technologies to the extent there are questions now or at the end. But the first five we're all sort of very familiar with. You sort of have wind and solar have become quite commoditized, although they don't really provide a lot of total energy in the global system today. Battery energy storage systems continue to be a potential solution, although I don't view batteries as energy supply because they are actually energy destructive. They take energy in and then they have some inefficiency round trip in order to deliver that energy, but they shift the time of which that energy is delivered. Hydropower, a fantastic resource, doesn't always get good press for whatever reason, but it is quite sustainable and renewable from a fuel perspective, but very location specific. Hydrogen is obviously hydrogen's a very popular fuel right now, frankly, in ways that I don't think make sense. But there's lots of stuff that I don't know, and there's lots of smart people pursuing hydrogen fuel and ammonia and other solutions that, I can't make the math work, but I think governments will likely subsidize many of these projects, and there will be some market. I mean, there exists a market today for hydrogen and ammonia, particularly for fertilizers. But the piece we're here to talk about today, and that I really made a choice based on my first principles evaluation of these different technologies to pursue in my career is nuclear energy. And we'll talk a little bit more about the history of nuclear energy, and I'll get into details on different technologies and what a nuclear power plant actually is. But fundamentally, nuclear energy is 3 million times more energy dense than fossil fuels. 3 million times more energy dense. Like it is such an order of magnitude more sustainable and more scalable than any source of power we've ever invented. That it's like a shame. It's sort of a spectacular failure that we haven't, as a society, been able to harness this and use it to grow our society. So we'll talk more about exactly what a nuclear power plant is. But I spent a decade in the energy space, and I didn't even appreciate how incredible of an energy source this was until I was forced to think about it critically. And so if you go to the next slide, all that to say, no one of these technologies on their own is going to create a both a sustainable and abundant source of energy. I personally believe nuclear is a step above many of those others, but we're going to need all of it. And we're going to need all of it at levels much greater than we've seen historically. So if you go to the next slide, Jimmy had his quote. This is the one that I like, since it reflects my journey and sort of my recognition that a decade in the energy space, and I had this huge blind spot about nuclear. It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so. And so it's been a good lesson and a humbling experience for me to remain pragmatic and open to new ideas and new ways of thinking and new perspectives. So with that, Jimmy, we can take over again and talk a little bit about the history of nuclear power.
Yeah, so we can't look forward without looking back a little bit. So go on, Vic, to the next one. So this is just a really quick thing. I'm not going to read all this to you, but this is just really kind of how we've developed it over the last 100 and some plus years. I mean, when you think about how fast that we were able to do what we can do, it's kind of amazing sometimes when humans, what we can come up with. And to Michael's point, the fact that we developed some of this stuff so fast, and then we've really hit a wall with what we did. But around the turn of the century, 1900 was when radiation was discovered, and the quote I threw out there about from Marie Curie was around this time. And from the time they discovered it, through Einstein's theories from 1905 up until the the Second World War, there was a big push to develop nuclear reactors. And actually, by the time the Second World War started, we had already developed a nuclear reactor. It was in Chicago. It works almost exactly like the ones that today with the fuel rods, with the fuel and the control rods that are inserted. It's kind of amazing that they were able to do what they were able to do from theory to practice. And then, of course, we all know what happened with World War II. All of that technology and all of our research was geared towards a weapon, which obviously the Manhattan Project, we know what happened there. And it ended the war. And then after the war, this technology, again, on all of our manpower, we went back to figuring out, or a lot of it, we know that they still continued down the weapons path, but there was a lot more demand and a lot more research into how can we do this for peaceful uses, and how can we create power, because we knew it was going to be a good way to create power and other things like steam, and we'll talk about too. But so between 46 and 60, say, the Navy became experts at nuclear reactors. So we talk about these new technologies. Michael and I, when we were going through setting this up, we talked about SMRs and people saying that's a new technology, but but really it's not. We've been doing these smaller nuclear reactors since the beginning. The Navy became experts at it, and out of that grew our commercial nuclear power industry. And from 60s into the 70s, there was a huge boom, in the growth of that, and we saw the potential and we saw what it could become. And then unfortunately in the 70s there was some economic issues, and then of course there was people in my generation, we always talk about 3 Mile Island, we talk about the accidents, but again, the accidents weren't what they were made to be. We might talk about that a little bit in the hurdles later on, but whatever happened with those, it did lead to some issues with regulations from the government, and which led to rising costs and just these extraordinary schedules to get these reactors built. So there was a huge slowdown in the growth between, from the 70s to just mid 2000s here, 2011. And of course, then we have another accident that really was not really a single life. I could argue maybe one we said that was lost during Fukushima, that accident. So when that happened, that decade from 2010 to 2020, actually we started seeing some contraction, like Europe in particular, and Japan shutting down all their reactors, and people were going to go away from nuclear power. Well, fast forward to 2020, 23, now we're starting to see, hey, well, that's not the answer. It's a little bit of a knee-jerk reaction, which again, as humans, we tend to do. I think now as a newer generation of individuals start looking at this, we're seeing a lot less negative perceptions. And then as we go forward, I think that we're going to see an exponential growth of this as this new generation and this really drive to have people understand what's really happening, really what we can get, like Michael was saying, 3 million times the potential there for power. Those things are just super important going forward. So this next topic is talking about current nuclear technologies. I'll turn over to Michael because he's really good about talking about this stuff, and he really knows he knows this very well. So, Michael.
Yeah, thanks, Jimmy. At least I know it enough for a finance guy or a recovering engineer.
Recovering engineer.
Yeah. I'd highlight, when we talk about nuclear technologies, we invented the first reactor from a napkin in 18 months without the personal computer. So, as a technology, nuclear is just a different way to boil water. And so if you think about it in that context, what we have here is sort of your general, what we call a process flow diagram. I'm sure you have similar concepts in the data center space. But really, we're just talking about moving heat through a system and converting heat energy into kinetic energy and ultimately into electric energy. And so in that context, a nuclear plant is the exact same thing as any other thermal power plant. So coal, coal, biomass, many natural gas plants. All we're doing is replacing the boiler with a pressure vessel. But the rest of the plant looks the exact same. And so if you go to the next slide, so, in this case, we have the coal plant on top and the nuclear plant on the bottom. And so instead of a chemical reaction where we're burning some sort of feedstock and delivering that fuel in a just-in-time manner, or in coal's instance, maybe it's 3 or 6 months in advance of burning that fuel, and then we need to dispose of that fuel in some way. A nuclear power plant just has fuel rods. They're static in a reactor vessel, and you flow water over them. And in the right balance, you can create an atomic reaction instead of a chemical reaction. And that reaction gives off heat, which is transferred from the water into steam and throughout the system. So if you go to the next slide, so then the question becomes, okay, from a first principles perspective, this is the same power plant that we've been building for 120 years with a core heat source technology that we've had for 70. Why the heck are we so bad at building nuclear power plants, right? And the truth is we've been terrible at it. And when we stepped back as an institution and was developing our business model, we interviewed over 1,000 people in the nuclear space across all different stakeholders, politicians, plant managers, utility operators. And we all kind of discovered the same thing. These projects had gotten bigger and bigger and bigger and bigger over time. And so they started at $10 billion and they eventually became $20 or $30 billion. And we found that that wasn't unique to nuclear, right? The larger the infrastructure project in the Western world, the greater the cost and schedule overrun. And so you often see them compared to Olympic stadiums, right? And the budget and schedule overruns that occur in these massive buildouts. Well, that has nothing to do with this simple heat source, and it has everything to do with the large project size, which if you go to the next section here, right? So this large project size results in an incredible amount of specialized labor, specialized supply chains, complex construction, and ultimately long delivery times. a couple of anecdotes that I think really demonstrate this problem. Hinkley Point C is a gigascale, large-scale nuclear project in the United Kingdom. And they have 10,000 workers on site any given day speaking 30 or more languages. So I don't know about anyone on this call, but I can't get like 4 or 5 people to get a project done on time and stay organized. You can imagine 10,000 people speaking 30 languages across an untold number of acres on a project site. It's no wonder it takes a long time. Just the busing and catering contracts alone cost more than our plant would to deliver. And the other anecdote that I'll use that I still think the nuclear industry struggles with today is every project loves to have the largest something in the world. And in fact, there was a microreactor developer that has the largest heat pipe in the world. In my experience as an investor, I don't want the largest anything in the world, the largest crane, the largest pool, because that makes it an engineering marvel. And frankly, engineering marvels tend to be expensive and take a long time. And so all of these things combine, if you click one more, Vic, to really the bottom line, right, which is increasing financing risk and cost. And the pesky little thing about compounding interest rates, that if you start with a $10 billion project and a 20-year delivery timeline, you're just going to accrue interest on that capital year after year after year. Okay, so we've identified and articulated what the problem is, and it has nothing to do with the technology or the heat source itself. And so if you click one more slide. So this is where we hear SMRs, or small modular reactors, as a potential solution. I have a lot of hesitation actually about the SMR nomenclature. In the industry, it's used to reference a whole number of size, scale, megawatt projects. And whether the reactor is modular or not really is immaterial. And so our approach, at least, is to eliminate research and development. So we don't want to take any component or technical risk, because anytime you do, it just increases cost and schedule. And then we build the plant. We borrowed this from the data center space, who sort of borrowed it from the oil and gas space, and the chemical processing space, which is true modular design, right? Which is constructing a power plant in a set of steel frames such that it can be built, QA/QC'd, and then delivered to site and assembled with minimal on-site labor and minimal on-site construction risk. And so that really is designed and has been proven to solve cost and schedule issues in other infrastructure projects, and in other infrastructure projects that do the same thing as our project, which is move heat through a system. So if you go to the next slide, I find this graphic quite helpful, although it's complicated. So what we've done is try to break it up into different sections, and I will attempt to simplify the language around all of the different names and technologies and brands that you see in the nuclear space. And so under this SMR umbrella, kind of in line with how many different types there are, the primary nuclear technologies are water-cooled. So what does this mean? So there are two types, there are two things in a reactor that we care about. The first is the fuel itself, what shape it's in, what its enrichment level is. The second is what the moderator is, or what is the fluid that extracts the heat from that atomic reaction through the system. And so I don't know the percentage off the top of my head. It's probably 85–90%, if not more, of the operating nuclear reactors are water cooled. And so you see a host of different technologies in that bucket. Vic, if you could go to the next. So then we have a breakdown between light water and heavy water. This generally refers to certain additives of that primary loop of the water that flows through the reactor in order to manage either the reaction itself and or pH levels and other water chemistry levels. So CANDU is a Canadian technology that's slightly different, and they're able to use a less refined version of uranium in their reactor. They've exported that technology to a few countries. Romania has a large CANDU nuclear power plant. But for the most part, most technologies are light water reactors. So light water, including boiling, we're probably at 80%, maybe 85 of the operating reactors in the world. So if you go to the next one, so then we have pressurized water reactor and boiling water reactor. And these are just general ways of how you maintain water or steam in your system. And so most of the technology, 70% of the nuclear plants around the world, 305 or so out of 400, are pressurized water reactors. So that means as the water is heated up, is heated up in the primary loop, it is maintained under high pressure in order to maintain it as a liquid instead of a gas. And so many of the SMR vendors or technologies, or sort of our peers, I guess, have this product. And we felt Last Energy, it was important because this fuel is readily available. So if you hit the next one more. So then under our SMR umbrella, right, small means different things to different people. Generally, micro is the 1 to 20 megawatts. SMR is sort of the full range of 20 to 300. And then there are a few firms that, they have SMRs, but their projects are really 300 plus megawatts, and, are now into the $3 or $5 billion range, which, in my mind is quite large, but to be fair, against a gigascale $20 billion project seems smaller. So that's the primary technology that exists today. And in my mind, the primary technology that we'll have moving forward. There's a whole other host of SMRs that fall under another acronym called AMRs, or advanced reactors. And so if you'll hit one more on this. And so these are generally non-water cooled. So all the different water that I talked about at a pretty high level that's used to extract heat, the non-water cooled use one of 3 different technologies, and one more, if you would. And so this is where you hear of like thorium or liquid salt, right? So that's sodium. You might have some metal, right? Some form of liquid metal that is flowed through, or high temperature gas. These are just different ways to extract heat from the reactor, put it through a heat exchanger, which turns water into steam and turn a steam turbine. And so you see a whole bunch of labels and brands across all of these different technologies and all of these different types of projects. So hopefully that suffices as a sort of 101 on different nuclear technologies as we think about the future.
Yeah, and then the future of nuclear power. This is where we start hearing a lot of questions about, how are we going to implement this? How much does it cost? And the cost prohibitive side, we hear a lot, cost and schedule. And of course, the regulatory side we'll talk about a little bit too. But Michael, I guess my question would be, what do you see the future of nuclear power? What do you think is the best? What's going to be the way forward for us, we think?
Yeah, my view, I mean, I'm biased because I'll talk my book, but it's a book I chose. Look, we have a playbook for deploying energy technologies in the market today. And this playbook was used first with gas-fired power generation in the 90s and early 2000s, then with wind and solar in the early 2010s. And it's being used today for batteries and hydrogen and all sorts of other crazy technologies. And so our perspective is that it's actually not a technology problem. I know I tried to give folks a background and articulate all of these different technologies. The truth is they'll all work. I mean, they all have operated in some form or fashion. What I think the nuclear industry needs to do is focus more on delivering value for customers and less on doing research and studies and new designs. And so the model that we're using is an energy as a service model. So we are a project developer. We'll ultimately be an owner and operator of our power plants. We believe in our product, and we believe we're best positioned to push forward on project development at pace and sell energy or electricity directly to customers that want energy and electricity, and finance the projects with capital markets participants whose job is to finance energy projects. I think you're actually seeing this model quite a bit in the data center space as well, where you have large institutional investors, Oaktree, Apollo, Brookfield, et cetera, right? They're coming in and they're investing in platforms, and then they're investing in SPVs to build out data centers. And we can do the same thing with energy and with nuclear. And so our whole business model is organized around this exact approach in order to be as scalable as possible, and in order for us to maintain control and speed around cost and schedule, respectively.
I found that very interesting because I didn't think of it that way till Michael and I started going through all of this, because I know for sure that a lot of our clients have investigated building huge solar facilities that they'll have a power purchase agreements. They're not going to run it, but they're going to help, be part of the power, using the power from those. So it didn't dawn on me about somebody wanting to do nuclear that way too. So it's kind of awesome to hear that. The next thing I guess we wanted
Jimmy,
to talk.
I can answer. Kelly's got a question on EPC, and it's a good one. And shame on me for putting an acronym in the slide, because we try not to do that for that exact reason. EPC is energy procurement and construction. And there, I could spend an hour on the different nuances and different ways to actually contract around the assembly and construction of the product itself. But generally, that's someone that's responsible for actually doing some of the welding and actually doing, the civil and site work, the electric connection work. So there's a whole host of subcategories within that. But it's a great question, Kelly.
All right. So back to hurdles for deployment. Thanks, Michael, for stopping me there. Sometimes I get on a roll and
It's okay.
keep going. But we had a lot of questions, pre-questions, and like asking us what are the what's holding us back from implementing more nuclear power sources in the U.S., and especially since we're such a drive to be green, and states like New York, who has their local law 97, which anybody that's researched that between now and 2029, there's going to be a big drop in the requirements there, because the state of New York is committed to getting sustainable energy sources that will help people in the city of New York City, to meet local law 97 by being able to have more sustainable energy. So it seems to me that's a no-brainer too for some place like New York that would want to have these nuclear facilities to help with that over this coming decade. So that was one of the things. And so, Michael, what do you see, I guess, as some of the bigger hurdles?
Yeah, I mean, so I'll be a little bit surprising maybe for folks. I think the biggest hurdle right now is the nuclear industry itself. I think the narrative, we're not good at telling a hopeful and promising narrative. It's sort of an aging, somewhat negative workforce, and generally it's full of engineers that just sort of want to engineer. And so you'll see these companies basically build up entire organizations designed to raise government funding to do research. And once you get the government on the hook with capital for research, that sort of ends up as a never-ending cycle. And so I think we see a lot of promising developments. I won't name names. I think there's some that I'm really rooting for, and others that I think are effectively the incumbents and just trying to sort of fleece the taxpayer. But I think that's the biggest hurdle, and people don't like that, right? I think that's the biggest opposition that I see is like, yeah, why should I give you billions of my taxpayer dollars because you can't build on time and on schedule? So I think that's the primary hurdle. I think here in the US, we do have some real challenges around our regulatory and permitting processes, and really a sort of a fanatical level of review that doesn't make sense. It's based on hypothesis that is continually proven, not to be true. But those are really entrenched interests. So our strategy, and I mentioned this right at the beginning, we're a U.S. company. We're developing projects exclusively in Europe at this point. Just the combination of a more efficient regulatory process and higher energy prices. And so hopefully we can demonstrate success and a track record there, and look to move back to the U.S. when it's a more accommodating market.
Yeah, it was interesting when we were going through this again, talking about our perceptions. Michael and I have some different perceptions about things, and I think it's a generational thing. Growing up during my generation, people were feared nuclear energy. First thing that a lot of people ask me about that's my age is when we talk about nuclear reactors, like, don't you worry about 3 Mile Island? Don't you worry about Chernobyl? Well, yeah, I mean, those were those were accidents. But in my mind, especially in 3 Mile Island and what happened in Japan, was it worked. What we were supposed to do, how we were supposed to stop these things from, impacting life. There was nobody died as a result of it in 3 Mile Island, and like we said before, you hear things like 15,000 people died in Japan. Yeah, but that was because of a tidal wave and a lot of other things. Nobody really died because of the nuclear reactor. Sure, they melted down, but they stopped it. And there can be arguments for years about that. I think, Michael, you had a perception about what it's actual versus projected, right? Or that people were projecting people were going to die.
Yeah, well, in Fukushima, it's pretty in Chernobyl, people use projections all the time. And so most of the counts that you'll see, whether they're rational or not, is immaterial. They're all projected. And I think now that we're 35 years, 37 years, some past, I think they finally decided that there hasn't been, besides the early responders that weren't given proper PP&E because the Soviet Union didn't have, workers protection, it didn't have OSHA. There really wasn't any effect to local populace, and even instances where there were higher, where there were perceived higher study rates or higher hit rates of certain of certain issues, they didn't manifest as symptoms, and so yeah, on the Fukushima side, the one what I always used to say is, I'll believe you're concerned about people if you can tell me the name of the earthquake. Um, it wasn't Fukushima, right? But it gives you a sense of the nuclear industry's ability, really to make it all about them, right? And to then use what news bias in order to drive revenue into radiation protection, as opposed to focusing on building new projects and creating value for energy customers.
Yeah, it was interesting too, because when I started talking to Michael about putting this together, I said, well, we're going to talk about, the safety concerns, and Michael actually says he uses the S word. He doesn't even say safety because he thinks, it's an industry that created its own pyramid of what they call disasters, basically, which is kind of overblown, right?
Yeah, well, yeah, the nuclear industry invented their own scale. Um, so you'll see things like it, this is, it's been deemed the highest nuclear accident, which sounds a lot more dangerous than, an asset loss that didn't harm anybody. And so, yeah, the IAEA has invented their own scale. And so I come from the oil and gas space, but you see ammonia and hydrogen, right? I mean, that stuff's really dangerous. And you look at you look at how people describe that, and they talk about the value, and they talk about it being incrementally safer than natural gas, which I'm not sure I buy. But you compare that with how the nuclear industry talks about itself, and it's a little. The other analogy that Jimmy and I talked about that I like is, if you've ever talked to a salesman that says, "Hey, I'm not going to lie to you," right? And they say that before every sentence. By the end of their pitch, you're pretty sure they just lied through their teeth to you. And using the S word is quite the same. And yeah, so I don't know. Look, it's my perspective. I certainly don't have all the answers, but it's been pretty interesting just to see the different mindset and mentality between the oil and gas space, kind of wind and solar, and the nuclear space. It's just been very different, and very different approaches, and there are ones that have worked, right? So
Yeah, I think like I was saying, my generation thinking about the accidents. The good news is that the younger generation, I hear them talking about this more and more, and they've not. Sure, they were Fukushima probably was there, but the Chernobyl and 3 Mile Island are like ancient history to them. They don't even think about that. So I do see a lot of positive. I guess the younger people, and how they look at it. And there was a movie we watched, Nuclear Now, that Oliver Stone put together, and they actually had some TikTok influencers and things on there talking about how they're trying to drive all these younger people to bring to bear pressure on their governments to hey, let's nuclear is an answer here. It's not unsafe. It's really not. It's a proven technology that we've been using for a long time. And when we started on the history, I talked about the U.S. Navy. The U.S. Navy's been doing this now for 100 years nearly, and they've had no accidents, to speak of. So it's kind of impressive, and it's a little disheartening sometimes when we feel like we're running into a lot of brick walls. But I do think these walls are going to be coming down over the next few years, because people are going to understand the technologies that we have today, which really work well, the solar and all that. It just cannot do it by itself. So I think as we put this pressure on the regulatory agencies and such, they'll streamline this process. And I think companies like Michael's company, who is talking about, we're going to build it, we're going to finance it. That's going to bring people together. And looking at it from a data center perspective, I think, we all know in this industry, data centers cluster. We see that in Ashburn. We see that in Washington State. We're starting to see it in other places. And I think these guys are going to all come together, and some company like Last Energy and Michael are going to be able to build nuclear reactors for these campuses that will be able to get onto these PPAs. And I think that's certainly something that could happen, and also utilities. I think that's going to happen too.
Yeah, Jimmy, maybe I'll just kind of note a couple of use cases that we're seeing, and we can open up for broader questions, but I think there were a couple pre-questions. So yeah, Jimmy mentioned the campuses. I would sort of bucket the data center use cases that we're actively engaged in developing to fall under three camps. The first is simple, is just a financial PPA or a virtual PPA. And so we'll sell into our electricity into the wholesale grid, but on the same grid as the data center customer. And really they're trying to get time matched carbon free power, right? Which has become a bigger and bigger focus, particularly as the hyperscalers have started to charge themselves an internal cost of carbon. The second use case that we're seeing is what we would call like a microgrid or a physical PPA. And I'll split hairs between this and the third solution. So a common one that we're seeing, particularly in Europe, but I believe it exists in the States as well, is there might be an existing, say, a 35 megawatt campus, but the owner wants to grow that to 100 megawatts. And so they call up the grid operator, and the grid operator says, "Sure, I can get you that capacity in 2038." Say, "Okay, well, shit, that doesn't do me any good." And so what we could kind of frame out there is basically deploying a 20 megawatt, basis 5 or 6 20 megawatt units, maintain N+1 reliability with our assets alone, and have N+3 reliability with just the existing grid connection. And ultimately, over time, we would want that grid connection, in place, but we can bridge that nose, the 5 or 10 years prior to that grid connection coming online in order to allow that customer to scale. And then the final use case that we're seeing is a little bit earlier stage because there's generally more participants, but sort of like what Jimmy was articulating, folks that are building data center and life science campuses. These are usually industrial developers themselves. They may have a large plot of redeveloped land that they're trying to build out, and they can't get power. And so we can be an anchor for not just data centers, but a whole host of energy intensive businesses like vertical farming, steel manufacturing. We could even use some of our, looking at using our waste heat for either preheat process steam or dumping into warehouses for air conditioning. You can imagine in North UK in the winter, you're opening the doors every 30 seconds. It can be quite helpful and energy efficient. So those are just a few of the use cases. I'm happy to articulate more in detail depending on what folks are interested in. But I think we can probably open it up for questions, Jimmy.
Yeah, so we'll just go to the next slide, Vic. We just wanted one more time. I hope, 45 minutes, we're not going to eliminate all the fear, but we hope we were able to at least give you a little bit to think about, to where maybe we can start to understand this technology a little bit better and fear it less, because I do think it's the solution. Okay. And now there's a QR code on there for a review. So if you guys could do that and evaluate our seminar, we'd appreciate that. But we'll open it up for questions if anybody has any questions they would like to bring up.
There you go. We did such a great job. They know it all.
Yeah. No questions? There was one question, the pre-questions, Michael, from about how this how this can work in, I think, in the utilities like steam and all of that. You mentioned that earlier, how we could tie into that with nuclear reactors are made for that, are perfect for that too.
Yeah, I like to well, there's a Tommy Boy reference that I like to use sometimes, and people are like, "Oh, could you use nuclear for this?" When he gives Tommy the refrigerator, and Tommy's like, "Oh, I could put beer or soda in there," and the dad says, "Well, anything you want to keep cool, son." And it's a bit the same with nuclear power. Everyone wants to like think that it's somehow different, but anything you would use heat from a heat exchanger or use electricity from a generator, you can power with nuclear energy. It's just the way to heat up water. And so yeah, the university campus question, um, physical scale. Oh yeah, from a size and density perspective. Well, let me talk about the technology first. So we have a steam bypass, but you could do it directly from the primary heat exchanger as well, and you would just take heat from what we call the secondary loop. So it wouldn't be going through the nuclear reactor at all. It would just be heated through a heat exchanger, and you could use that for district heating or absorptive chilling. And depending on the temperature, right? So the heat as it moves through the system, generally as it loses its potential energy, the heat value is less. And so depending on your use case, you could take it out from different aspects. And then yeah, the physical scale. So this is where SMR is a pretty critical or not a helpful distinction, because if an SMR can be 500 megawatts or it can be 5 megawatts, it is meaningless on the amount of acres that they need. We generally, one unit is about the third a size of a football pitch. Maybe 50 by 100 meters. Sorry, most of my stuff is in metric because we're developing in Europe. But yeah, for super dense circumstances, we would need some regulatory progress to be a little bit less conservative. Although we have found certain instances where there is more land than you would think available, and we're able to pipe over some distance, right? Not a long distance, in order to serve heat customers. But we can go further over electricity. So yeah, hopefully that answers your question, Kelly. There are reactors that could be located or sited within 10 acres, and then it just depends how many megawatts you would need. Okay, let's see. Not a question, comment. Well, thank you, Michael. How have you found it with companies for the cost of building it when they usually look for a 3 to 5 year payback? I'm not sure which angle you're looking at there, James. Maybe I'll split the two customers that we have, and correct me or add a note if this doesn't answer your question. So when we're selling electricity to customers, they don't have a capital expense at all. So they're looking at it as just an operating expense. Are they saving money versus their expectation of future power prices, or do they have value by having a fixed price of power? Or can they not get power at all? And then they're a little bit less price sensitive, but they're able to get the product that they can get. So they're not looking for a payback on capital investment. On the project investor side, so this is the debt and equity that we use to fund the project based on the projected cash flows of that long-term power revenue. And generally, they're not looking for such a high 3 to 5 year payback. On the conservative end of infrastructure investing, it's 5, 7, 8%. So that's obviously much longer than a 3 to 5 year payback. Our projects are approximately 7 to 8 year payback, so it's a mid-teens unlevered project return. And so that's really a premium to other technologies, right? Wind and solar has been commoditized and pushed down to that 5, 6, 7%. But we think that's important as we kind of prove out the business model in order to attract that capital. So I think that's what you're asking. Hopefully that addressed your question. Okay.
Next one's about waste stream.
Yeah. If you speak about any waste stream hazmat end users would have to plan for accommodating. Yeah. So good question. Yeah, waste stream. So yes, we do have spent nuclear fuel. We don't move that spent nuclear fuel during the operating period. So instead of doing what many other reactors, like the large scale reactors do, which is every 2 years, they open the reactor, they pull out, they replace a third of the fuel, and they shuffle all the existing fuel, and then they have to move the fuel around. We put the fuel in our reactor, it stays there for 6 years, and then it stays in its cask underground for the full useful life of the asset. During that asset useful life, we fund a reserve account over time in cash. So it's not a letter of credit or a parent guarantee like many other technologies. And then we fund whatever the country does with their spent nuclear fuel. I could talk about spent nuclear fuel for a long time. Suffice to say, really the risk is what we call decay heat. After 7 years, that decay heat has exponentially decreased to a point where it's not terribly warm. And we say warm, we literally mean temperature warm. And then you can put it wherever you want, but it is pretty harmless unless you eat it. And I would also like to say that it's a solid. So the Simpsons like to show it as like some green goo, but that's just not the case. It's a solid rock. It was a solid rock pellet to begin with. It's a solid rock pellet on the end. And so historically has never harmed a person, place, or thing. And I think it's actually, many people point to waste as the problem with nuclear energy, and I would argue it's one of its greatest strengths. Because it is so much more energy dense than alternatives, there is incredibly little amount of waste considering the amount of energy consumed, 100 times less waste than alternative sources, and it is fully accounted for, and it's probably the only technology that has that. I won't. We could take more time, but I won't go further. Hopefully, that addresses that question.
Yeah, it was funny. I just wanted to add there the thing I had heard during when I was researching this was all of the nuclear fuel, spent fuel that we've used in all of our reactors for 70 years could be stored in a big box retail store. So you think about that over 70 years, 20% of the power we've created in this country for 70 years, the spent fuel could be there. And think about the impact on our environment from fossil fuels is way it's just funny that we even have this conversation.
Yeah, the Netherlands does it the best, I think. They actually put their nuclear fuel in the same building that they house all of their nationally owned art. So it's a museum, and you can come and you kind of see the art, and it makes it less scary for people because they can see what it looks like, and it sort of demystifies it. Anyway, that's one of my coolest. That's the country that I think does it the best. And then Dustin's question. Yeah, we have not. Well, it split hairs a little bit. We are not developing any projects in the United States, and so we are not engaging with the Nuclear Regulatory Commission here in the United States. Every country where we're active has all of the appropriate treaties, and they have their own nuclear regulatory agencies, as well as the traditional permitting and license and local stakeholder engagement processes that we've been very active with. And so we're engaging with those agencies and have been for the last 18 months. Well, maybe longer than that, actually. We are there is some nuance around parts of the NRC where we have to give notice when we share technology and some of those types of things. So there is a light touch involvement with the NRC, and we're certainly involved with the DOE here in the U.S. Around some of those requirements. But we aren't doing some of the NRC processes that you've seen from other folks in the space.
I think that was the last question. So unless there's any other questions, I think we can give everybody 5 minutes back. But we really appreciate it. Anybody that took the time for this, we like I said, can't tell you how much we appreciate that. We will be able to share this. That was a question too. This has been recorded, and we'll be able to share it with everybody that attended afterwards. So, and people that were registered and missed it, we'll make sure we get it to those guys too. Michael, any closing thoughts for you?
No, I appreciate the invitation to at least share my perspective and thoughts. Like I said, I don't have all the answers, not by a long shot. And really appreciate everyone's interest and willingness to listen. So thank you.
All right. Thanks, everybody.